Okay, guys, we are continuing class part 4 of the linear system theory. And the previous class, we saw that if you have homogeneous state space equation, means that there is no u, there is no control input because it was ax plus bu. So the name of this homogeneous differential equation, as you know from undergraduate control. So, and we saw that the solution gonna be this x of t we derive together, which is at x of at the initial condition times 0. We derive together that this is sum of k from 0 to infinity matrix a to the power of k tk divided by k factorial and x at this at times 0. That's right. And we established some properties for the matrix exponential. So the name of this was matrix exponential if you look at the previous notes. And we said that the first time derivative of matrix exponential, as we derive together based on the Taylor series expansion, it is a EAT. That's right. Remember that we got together. And now let us do this through the Laplace transform Laplace transform. We solve this. Remember, in the undergraduate control, if you had such a first order differential equation of x dot is equal to ax, and you apply the Laplace transform to transfer from time frequency to time domain to frequency domain, by assuming that x naught is not 0 here this time. So you're going to have x of s minus x at time 0 is a x of s. Remember, this is the first time derivative in undergraduate control. So, and on the other hand, you can say you can write this as s x of s minus a x of s is equal to x at time 0. So x of s gonna be s minus a, gonna be x at time 0, and so x of s, the solution in the frequency domain, is x at time 0 s minus a, right? So now, but this is not useful for us because we have to go back to the time, so that's why we have to apply the inverse Laplace. So having that, you get x of t gonna be, and the Laplace inverse of this 1 over 1 is EAT. These are the undergraduate control at time 0. That's right. Now what we have here is the state space equation, extended version of that. So you're gonna have x dot is equal to ax, the homogeneous state space for the LTI systems. So again, what we're gonna do, we're gonna apply the Laplace transform, and what we get is x of s minus x, because these are the state variables. That's right. These state variable vectors is a x of s. So now moving that, x of s. Now moving that to other side, you're gonna have, see, and you're gonna have x of s. You cannot leave here as s like here. That's right, because you are dealing with the matrix. So s I identity matrix minus a, right, is equal to x at time 0. And you cannot divide this both sides by this because you are dealing with the matrix. So what you're gonna do, you're gonna divide the both sides by what? By s minus a inverse. These are matrices. That's right. So what you're gonna have, you're gonna have the solution x of s is x this, x this, x at time 0 si minus a inverse. Again, this is not useful for us because we're going to find the time solution of that. So what we're going to do is this again. So x of s, the vector of state variable, is again x at time 0 si minus a inverse, right? So what you're going to have, you have to apply again what? Laplace inverse. Here we go. Laplace inverse. So what you're going to have? You have x of t is x of 0 at Laplace inverse of si minus a inverse. Bingo. Why bingo? Because we previously, guys, solved this state space LTI system, homogeneous version of that, and we got this solution, right? I'm just putting here. Look at here, guys. So we got this solution. X of t is x as 0 EAT. So we are not blind. So we can conclude that the matrix exponential EAT, matrix exponential, is this si minus a inverse. Bingo. This is very important, guys. That's right. This is how we calculate by taking that to the Laplace domain and then backing that by Laplace inverse to the time domain. Understand? So we got the solution of that. And we know from the trivial algebra that if you remember, si minus a can be written as I over a plus a over s square, I over s, I'm getting over, plus a square over s cube, and forever. See if you can prove this. This is undergraduate relation. Understand? So, after knowing this, that the matrix exponential is this function, so let me introduce state transition matrix, right? So again, we have this homogeneous state space LTI system. That's right. So we can write its solution as what? As x of t is equal to phi of t and at x at 0. Similar like these. That's right. And phi, I name it as state transition matrix. Phi of t is n by n matrix such that what? Such that phi at time 0 is I, identity matrix, and the phi dot of t is a phi of t, that's right, and the phi of t is a matrix exponential, which is L minus 1 si minus a inverse. Here we go. Understand? So what is that starting with you guys? Yeah. So x of t is this. Understand? So if you put from whatever I defined here, x of t is phi of t x at time 0. If you put at time 0 everything, time is 0. You get x at time 0, phi at time 0, x at time 0. Because phi at time 0 is I, so what you get is, obviously, x of 0 is x of 0. Understand? So now if you have the time derivative from this, d over dt from the both sides, d over dt, what's happening again? This is getting warm. I love you, Microsoft. Okay? In selling they are excellent, in working they are horrible. Okay? So x dot, see how it's working. X dot of t is equal to phi. Let me fix this, guys. So x dot of t is equal to phi dot of t at x0, but we know that x dot is equal to a x of t. That's right, origin get here. There we go. That's right. Understand? So, like as the metric exponential, note that this is phi dot. Note that inverse of state transition matrix is equal to E minus AT, or you can write as this, minus T. Here we go. This is another relation that you have to know. Understand? So
I can learn to understand you much better.
Oh, okay. So when I say, guys, phi matrix transition at time 0, which is E a time at 0, that's right. So means when time is 0, means that we have a kind of impulse and every term will be simply, will be identity matrix. So that's why we say phi at time 0 is E a at time 0 is I. I'm just talking about this. Right? This is a very simple interpretation of the phi at time 0, or matrix exponential is at time 0. So likewise, the exponential matrix, we have some properties for the transition matrix. So 1, phi t1 plus t2, which is exponential matrix A t1 plus t2, as we know from previous class, is exponential matrix A t1, exponential matrix A t2. This is equal to phi t1 in phi t2. or it is equal to phi t2 in phi t1. This is one property. This goes to this. Okay. 2 phi t to the power of n, that's right, is equal to phi of n t. This is very straightforward, guys. You can prove it by yourself. 3 phi t2 minus t1 in phi t1 minus t0. Let us do that together. This, based on this, gonna be e a t2 e minus a t1 e a t1 based on whatever I have done here, remember, in e minus a t0. We are not blind, so we know that, oh my god. So we see that this is how much? I, not 1. These are matrices, that's right, I, right? So what you get is E A T2 minus T0, right? Which you can write based on relation number 1 as phi T2 minus T0, that's right? And you can, this goes to here. Understand? So this is another things that you have to do. Now let's go to examples. Example. Suppose you have x dot is equal to 1, 3, 0, 2, x. Oops, what is this? Right, in x. This is homogeneous LTI system. Oh, let me fix it. And x. I don't know. Let me put here, huh? I don't know why it's not working. You have to appreciate the Microsoft Pro. X. Okay, whatever. So this is your A. Let me go to the next page. Maybe mistake is here. See? So example, this x dot is equal to, yes, it is 1, 3, 0, 2 in x. This is homogeneous LTI system, that's right, and this is your A. Now the question is calculate phi of t, or matrix exponential state transition matrix. But as I taught you, phi of t is matrix exponential, and we derive together as Laplace inverse of Si minus A and inverse. So what we're going to do, we have to calculate all of them one by one. So what you're going to have, Si minus A, it is Si, S multiplied by identity matrix, and because it's a second order system, 2 by 2. 0, 0, S minus matrix A, which is 1, 3, 0, 2. And what you get is S minus 1 minus 3, 0, S minus 2. Now what you're going to do, you have to calculate its inverse, that's right. This is the inverse of, you have to calculate. So inverse of this matrix, minus 3, 0, S minus 2 in inverse. So you're going to have S minus 1 minus 3, 0, S minus 2 adjugate divided by determinant of this matrix. It's going to be simply S minus 1 in S minus 2. we know for a 2 by 2 matrix, I told you previously, adjunct gonna be what? Changing the diagonal, s minus 2, s minus 1, and reversing the sign of the non-diagonal elements, right? This is the general rule for any second 2 by 2 matrix. So on the other hand, Si minus A inverse gonna be this, S minus 2 divided by S minus 1, S minus 2, 3 divided by S minus 1, S minus 2, 0, S minus 1 divided by S minus 1 in S minus 2. This with this goes to New York, this with this goes to Denver, that's right. So the result gonna be 1 over S minus 1, 3 divided by S minus 1 in S minus 2, 0, S minus 2, right? But you have to use the inverse Laplace to calculate the state transition matrix. So what we're gonna have, Laplace inverse on this, Laplace inverse on this matrix. But if you remember the undergraduate control course, we know that the Laplace of E plus minus AT, it is 1 over S minus plus A. This is plus minus, this is minus plus, right? Right? So exactly here. So comparing that with this, the Laplace inverse of this gonna be how much? Yes, E T, because your A is 1. This is gonna be how much? E2t, because your A is 2. Now you have to calculate the Laplace inverse of this term, right? Is it recording? Yep. So doing that, three over S minus 1 in S minus 2 can be done by S minus 1 plus B in S minus 2. So you can use the residual of this function. I mean that you can say A is S minus 1 multiplied by this term at S minus 1, because there is not repeated poles or roots. At where? At S minus 1. This with this goes to hell. So what you get is 3 divided by minus 1. A gonna be minus 3. And the B gonna be S minus 2. Again, divided by the whole term. S minus 1 in S minus 2. This with this goes to hell. At where? At this pole. Gonna be 3 divided by 1 is 3. So this term gonna be minus 3 divided by S minus 1 plus 3 divided by S minus 2. So now you can use this relation, and as we did here, right, for this and for this, you can easily see, let me change the color, that the Laplace inverse of this term gonna be minus 3 ET, and Laplace inverse of this term gonna be what? 3 E2t. Understand? So phi of t, or the transition matrix or matrix exponential, is from this gonna be e power of t here, 3 e 2t minus et, right? Because they are this minus minus this plus this, right? 0 from previous page, and e 2t. Bingo, you got that. Understand? So you're gonna tell me, okay, what I have to do with this. So guys, remember that original, the LTI second order system was this AX, and your A was what? Your A was this, right? So we know we calculated that the solution of this, for God's sake, x of t is going to be e at in x at time 0. Now I'm telling your system, so this can be equation of the motion of a mass spring and damper. That's right, mass spring and damper. If you pass the vibration course, obviously you know this. For example, I'm saying, okay, it can be whatever. Okay, so you have two state variables, x1 and x2, position and the velocity, because your system is 2 by 2. Remember the vibration under graduate control? Okay, so on the other hand, you can say x dot 1 and the x dot 2, the solution is e, what was that? T 3 e 2t times t's time et 0 e 2t, right? In what? In initial values, x1 at time 0 and the x2 at time 0. Here we go. Based on this, oh, sorry guys, I mean the solution, not that. I'm getting over. Right? x1 at time 0. See, this is the solution that we got together. That's right. So this is, here guys, this is 80 and etc. So again, this is matrix exponential. Now if I say, for example, if the initial values of the state variables, means the position and velocity, or the pressure and pressure dot, or temperature and temperature dot, here is 0 and 2, for example, I'm just giving. So you can find x1 and x2 as et 3 e 2t minus et 0 e 2t in what? 0 and 2. And so your x1 and x2 becomes this by this 0, this by this 2, 6 e 2t minus et 0 and t e 2t. And obviously your system is unstable. Your system is unstable. Your system is unstable. Why? I'll give you 1 minute to think about this. Yep, it's recording. Why your system is unstable, guys? Why your system is unstable? Yeah, because when time increases, all of this goes to infinity, and your response is not bounded. So your x1 goes to infinity, x2 goes to infinity. This is your function as control, and you're going to fix this. By what? By adding a controller. BU. Okay, U control. Understand? So now, as homework for yourself, calculate state transition matrix phi of t for what? For a 2 minus 4 and 1 5, and find the solution x of t when this is minus 2 minus plus 2. What are these? These are x1 at time 0 and x2 initial conditions. Are this? Find this for me. Okay. And if the A is a third order system, 1 2 3 minus 3 0 1 5 6 and 7. So find again also, after finding phi of t means matrix exponential, okay, find the solution when x at time 0 is minus 2 0 and 3. Find the solution for this LTI, homogeneous equations. Okay, understand? So now, after dealing with the homogeneous LTI system, x dot is equal to ax, right? So we have to go to the real case when you are designing solution of non-homogeneous state equations. So remember that this is the first order differential equation, x dot is equal to ax plus bu, or when it goes to the state space equations, you're gonna have x dot is equal to ax plus bu. Okay, for going to this, I have to remind this from differential equation course. Remember, so from hold on. Okay, so from differential equation course that you had undergraduate, you know that if you have this equation, x dot minus ax plus bu, its general solution can be written as this. This is from the differential equation. X of t is 1 over p integration of ph dt plus c over p. This is general for the first order differential equation. That's right. So we know that, for refreshing your mind, that p is exponential of minus a, this minus a in dt, that's right, and the h here, h is the force controller that you're applying to the system, bu, this, understand? And the c is constant that you're going to determine using what? Using the initial conditions. Okay, so now let us do that here for the general first order differential equation. So x of t for the first differential equation, 1 over p. P is what I told you is this. So because this is constant, oh, hold on. So we called a is constant, comes out minus a integration of d. Oh my god. So integration of dt, which obviously is e minus at. So your p is minus at. So what you're gonna do here is e minus at. Integration. This p again. E minus at in h. H is bu here. That's right. H is bu dt plus c divided e minus at. Again, just c over p. Get you guys? C over p, right? So x of t, I'm taking this up, e plus at integration of bu e at dt plus c e minus at, right? So now let us say we want to calculate c. So look at you guys. Okay, I said that c is calculated based on at time 0. At time 0. So we're gonna have the at time 0 x of 0. Okay. E to the power of 0 is 1. Integration, this is from 0 to t, that's right. 0 to t, obviously. So a 0, okay, at time 0. So whatever is inside, bu e 0 dt, there is no, this is going to be 0 plus again c e to the power of 0, which is 1. So you get from here that the c constant is x at time 0. Because there's integration means sum. Sum from time 0 to 0 is 0. That's right, obviously. This is basic mathematics. That's right. So the general solution for that differential equation gonna be what? Gonna be?
I can learn to.
Oh, I don't want to let you learn. EAT from 0 to t. E minus a tau. I'm just changing the variables to make difference between this time and this. That's right, because we're integrating here. Bu d tau plus c e again plus at in cc is initial condition of your variable. Here we go. This is the general solution for this differential equation. Now we are using this to go to LTI systems that you have more than one variable. You have the state variables here. That's right. You see. Okay. So there we go. Okay, so I'm gonna stop it here because I have to go deep to the mathematics here. Okay, that's it. See you next week. And I gave you the homeworks, that's right. Let me see. Homeworks. What is this? Okay, I gave you homeworks. Okay. everything I needed? No. So see you next week, guys.